Welcome to this second video about flow in long subsea gas pipelines. As for the first, just like the first video, we will use subsea pipe 1 as the example pipe we will simulate. But in the first video we looked at steady state simulations, while on this video we will look at transient ones. And that will help us answer questions like, well, let's first look at what the line actually looked like. This was explained in greater detail in the first video, but for those who haven't seen it, it was the world's longest line when it was created, and it goes from a place in the North Sea, from a platform there, and it goes all the way down to Zeebrugge, and it is 814 kilometers long, and it was commissioned in 1993, and it was the world's longest at the time. Some of the interesting questions we will be focusing on is, why do we actually do transient simulations? After all, we saw that steady state simulations in video 1 gave us quite a lot of answers already, but there were some answers it couldn't give us, we will see, and we will see why. We will also look into whether transient phenomena affect the capacity of the pipeline, because the capacity is of course one of the big parameters. How much gas can we squeeze through there? And we wonder, are there any problems the transients can create in gas pipelines? Transients tend to be less problematic in gas pipelines than in liquid ones. For instance, in water pipelines, transients can create very high pressures. They don't really do that in gas pipelines, but there are some problems anyway that they can create. We'll fire up Flowline Pro and do a transient simulation. For simplicity, we started by opening an existing case. We showed in the first video precisely how to define a case. So now I just open it, the subsea pipe steady state simulation of the coldest month, which we did on the first video. And I reset the simulation results, and I come back to how I define my system. I defined the pipeline in detail. You remember this menu, the elevation profile and how thick the pipe is and so on. Everything is in there. At the inlet we had a defined pressure. It was 14.9 megapascal continuously at the inlet. Let's keep it like that for now. At the outlet we'll modify it a bit. We had a constant mass flow out of the pipe there, but we will now say that the first hour of simulation it will stay constant. So an hour, that's 3,600 seconds, and we simply take the same mass flow, 382 kilograms per second. Stays the same, but after that, during the next hour, so that will be up until 2 hours multiplied by 2, that will be 7,200 seconds. The mass flow goes down to 0. We do not change the temperature at the outlet. It doesn't matter anyway, because the gas goes out there, it doesn't come in at that end. So first we keep the outlet mass flow constant, and we linearly reduce it to 0 during 1 hour, and we keep it there for the rest of the time. And we have set this up now to run for 24 hours. I'll show in a minute how that is done. Let's run it. First the steady state simulation, and after that a transient one. So there goes the steady state simulation. It is creating starting values for the transient simulation. And now goes the transient simulations, 24 hours of pipeline operation. And that goes pretty fast here. It takes, I think, less than half a minute to simulate 24 hours of operation. So this is very, very fast simulation. And there the results are finished. Let's start with showing the elevation profile again, just to repeat that. It starts 40 meters above the sea level, this line on an oil platform. It goes straight down to the seabed, and then it gradually rises towards the point where it comes into Belgium here, above sea level, of course. Perhaps we should see the burial depth as well. It is almost not buried at all near the platform, but then a survey has shown that it has become partly buried and actually fully buried near the outlet. So that means we have better thermal insulation near the outlet, because the pipeline is almost fully buried most of the time there. Now the results in pressure, for instance, this we have seen before during the steady state simulations. We have the inlet pressure we said should be 114.9 megapascal, and near the outlet we get, in this particular case, it says 8.3 megapascal. That was initially. We can change the time by using this little slider here down in the left corner, and I now increase up to 1.7 hours and up to 2 hours. Now we remember we have closed the outlet end, and that leads to a gradual increase in the pressure. We see the scale jumps a little bit, the curve jumps. That's just because he rescales all the time, so that we use the full window for scaling. So after 24 hours, the pressure turns out to be pretty constant throughout the pipeline. It's approximately 14.9 megapascal in the whole pipeline then. Pretty constant through the whole pipeline. We can also make a time plot here. So at the beginning there is no change over time at the inlet, because we kept the pressure there constant. But if we go into the pipe, now we are 44 kilometers into it and so on, and we can go to the very outer end. This is a time plot of the pressure near the outlet end. Remember, for 1 hour we kept it fully open, then we closed it, and the result of that we see is a gradual increase in the pressure near the outlet. But interestingly, it has not stabilized 23 hours later than we started the closure here. So it takes more than a day to stabilize a change we make in this very long line. What about the mass flow? How does it develop? Mass flow we have here, and we start out with the axial plot, let's say. So the initial mass flow, we see the scale here. It looks like a little jump, but it isn't. We see it's basically the same number on all the scale is such that this is really a flat line. It's only a small deviation from that. And let's see how this develops over time. Here we have come to 1.7 hours. So remember, it was after 1 hour we then we close the outlet end, and then the mass flow near the outlet starts to go down. So after a while, obviously the outlet mass flow becomes 0, and as time goes by we get close to 0 mass flow in the whole pipeline, but not quite. We still have more than 60 kilograms per second going in at the inlet end. Maybe better to look at the time plot, and this is the inlet end of the time plot. So at the beginning we had the same coming in as went out, namely 380 kilograms per second, but then after we close the outlet end, that begins to have consequences near the inlet end, so slower and slower we get less and less mass flowing in. But we see it hasn't become zero even after a whole day. The temperature could also be interesting. Go for the temperature here, and let's also see the outside temperature. The sea temperature is the blue line, and the red line is the gas temperature inside the pipeline. And here in the near the outlet, the gas, due to the Joule-Thomson effect, as it expands, the gas becomes quite cold. It's also good thermal insulation there, remember, because the pipeline is buried. But as time goes by, what happens? Well, after we have closed the outlet, the gas temperature goes up a lot. That's quite interesting. Look at that. Now the temperature is actually higher, the gas temperature is higher in the whole pipeline after we have closed the outlet end. And that's the situation after 8 or nearly 9 hours. And then it gradually falls down again because it's cooled by the sea. A time plot can be useful there. Let's look at the temperature near the outlet end. Just after we start closing the outlet end, it begins to go up, and we remember after 2 hours, that will be here approximately. We then got a lot of the temperature goes up, and it reaches it almost reaches 300 Kelvin at the maximum. And why is that? What's going on here? Well, the part of the gas which is captured in the gas pipeline when we close the outlet valve is being compressed more and more. And compression, when we compress a gas, even a perfect gas, it becomes hotter and hotter. So that compression leads to the temperature going up. And that continues as the pressure goes up more and more until we reach a point where the temperature loss to the environment becomes higher than the further increase due to the pressure still going up. We remember here at the last part when we looked at the pressure, can go back and look at the pressure. No, the pressure we had here. This is the pressure at the outlet. We see the pressure goes up all the time, but it doesn't increase very fast here. So then it turns out we are losing heat faster than it's produced by the compression. So we reach a maximum temperature. Not the problematic temperature, so there's nothing really to worry about here. But what these simulations show actually is that the mass flow became pretty constant. If we look at the mass flow near the inlet end, yeah, that's what we have here now. The mass flow does not stabilize in a day, but the pressure more or less did. So here we have the pressure, and we have let's look at an axial plot of the pressure. After the full simulation, we see that the pressure is almost the same in the whole pipeline. So that means the reason why it hasn't stabilized cannot be because of the friction, because the friction would mostly make sure there is different pressure along the pipeline due to the frictional loss. But there isn't much of a frictional loss. So the parameter making it so slow to get stable conditions in the pipeline isn't so much the friction as it obviously is the thermodynamic condition, the heat loss from the pipeline. So losing the heat after we have closed the outlet end takes much more than a day, while spreading the gas in there so that there's almost no pressure loss, that goes very much faster. So the insulation of the pipeline, we can then conclude, is the main parameter. The thermo-insulation is the main parameter in deciding how fast it responds and how fast it stabilizes to changes. What is going on under the hood of these simulations? Maybe the easiest thing to do to have a closer look is to simply close the program and we restart it again. And let's start with the same case, the steady state coldest month, and then reset it again. We are back to the original settings, and we'll have a closer look at the settings because it tells us something about what's going on in the simulation program. It says here we can choose between various mathematical models which are being used during the simulation, a conservative and a non-conservative formulation, for instance, or we can have an automatic switch between the two. What that means is described in the manual more closely, but this tends to be the fastest one, but not quite as robust as the conservative mathematical model. We use only 100 cells when we do the calculations. That means we split the pipe into only 100, which isn't much for such a hugely long pipeline. But by doing more simulation experiments here, we can actually increase this number to get higher accuracy. But we will see that we get basically the same results anyway. So we don't need more cells than this. The fewer cells, the faster it goes, but also the less accurate numerical accuracy we are talking about here. And some plotting parameters and some automatic error control for the numerical integration we can specify. And of course how long we simulate. This is 86,400 seconds. That's actually 24 hours we have specified here. The integration method can be specified. Most of the time we use an explicit Runge-Kutta order 4 with an order 5 method for step control. Those are details we don't need to understand, but which is important when you create the program. You don't really have to change any of these settings. It will work as it is. And also you can choose between various ways for the discretization in space. Again, you don't really need to know that. And the CPU also, we can change the setting there. We can try a simulation now with a higher number of cells. Let's say we double it to 200. Then the simulation will go slower, typically a factor 4 slower when we double the number of cells. Let's say OK. And now we do a simulation with constant inlet pressure and constant mass flow out of here. And we run first the steady state simulation. There comes the steady state one. And followed by the transient one, which is now somewhat slower because we have more cells. We can look at the computer's task manager just to get an impression for how much CPU it uses. It uses parallel processing. We can see there are 8 cores in this particular computer. Or actually it's 4 cores, but it's split cores, so it looks like 8 CPUs, and it uses it pretty much to the maximum. We have 75%, 83%. It's around 80% of the CPU capacity of this computer is being used now, and that speeds it up by a factor of almost 4 compared to if we do not have parallel processing. So that makes sense to use parallel processing. Okay, there we finished. Now look at the pressure again. Remember, we have as a boundary condition a constant pressure at the inlet, but we do not have a constant pressure at the outlet. We have a constant mass flow. So let's look at the time plot at the outlet. And what we are interested in is how much does the pressure change when we go from the steady state beginning and out to what we end up with after 24 hours of transient simulation. We do not expect this to change at all if the transient and steady state simulation agree with each other. And that's also what we see here. It's 8.28, so 82.8 is the pressure out according to the steady state simulation, and 82.9 is the pressure out according to the transient simulation. So that's very, very small change. So it means the two different calculation methods, the steady state and the transient one, when we run the transient one in such a way that it is comparable to the steady state, they agree very, very, very well with each other. And that's a good way to, one of the many checks we can do to see that the simulation program works well. We have now restarted Flowline Pro again, and we will define the system the same as before. We take the coldest month, and but we will change the outlet boundary condition somewhat. We will now try to simulate a more typical gas consumption down in Belgium. Suppose zero time is 12 o'clock at night, midnight. And suppose the mass flow at that time is 200 kilograms per second, and it stays like that until 8 hours later, 8 o'clock in the morning. So that is 28,800 seconds later. It's still 200 kilograms per second. But then during the next hour, which then stretches into 32,400 seconds after midnight, suppose it then is increased to 400 kilograms per second. This may be more or less typical, that when people wake up, they go to work, the gas consumption increases. Now it's a bit more complicated than that, because there's a network there, there's LNG terminal and other things, so this is not the only gas source, but let's simplify a bit and suppose this is how it goes on. And then it stays high, the consumption, until 4 o'clock at night, we presume, and then it is gradually turned down again until 5 o'clock, where it's down again to 200 kilograms per second. And we repeat this pattern for 3 days now. So I have prepared this on an Excel sheet, so I just paste it in. I go here and I paste in those data. There we go. So what this shows is simply the mass flow going up and down several times during those 3 days. And we will simulate it, but then we have to of course simulate for 3 days, otherwise we don't get all the information we are interested in. So we go up to 3 days, that is 259,200 seconds. Let's simulate it. Steady state simulation going on. And here comes the transient simulation. So what we are going to test in this case then is whether the pipeline has the capacity to store enough gas for the consumers to get the gas they require. We have already seen that the maximum we can get through here on a normal condition is something like 380 kilograms per second. Now we are going to take out 400 kilograms per second during a large part of the day, which is more than we usually can push through during steady state conditions. But on the other hand, we take out less during nighttime. There we go. Let's start with the pressure profile again. Here is the pressure profile at the beginning. and it makes most sense, I guess, to make a time plot here at the outlet. Here it is. We see that the pressure is quite high at the beginning because we take out little gas then, but then it falls during the high consumption period at daytime. And then once we reduce the consumption, the pressure gradually builds up again. And this repeats itself a few times. And we see the peak pressure actually goes down over time because we started out with a pressure which was very high because we did a steady state calculation then. So this would have gone gradually down more during time, but we see that we are still we are way above 10 megapascal, which is much more than the contract specifies. So we can operate the pipeline like this for a very long time. And also if we for some reason took out quite much more some of the days, that should also work quite well. We would still be able to keep our guarantee. So the storage capacity of the pipe is very significant for some types of operation. May have a look at the temperature also. Let's do an axial plot of the temperature. We see it jump somewhat up and down at rescales also, so it becomes a bit confusing, but we can see the temperature goes up and down. Maybe we do a time plot instead. This is 31% into the pipe, so that's 256 kilometers into the pipe. The temperature will look something like this. It isn't much of a temperature difference. We see the scale here. It's very, very small differences between maximum and minimum temperature, so it's not really significant at that point. But once we get closer to the outlet, the temperature changes are a bit more significant. So we see the highest temperature we will experience then is 282 Kelvin, something like that, and the lowest are 272 Kelvin. We could look at the ambient temperature as well. Well, then we came back to the axial plot again. Here we go. So for the most part, it's going to be colder than the sea temperature, even at the outlet end. But we will, at some points in time, have slightly higher capacity. Could be interesting to look at the mass flow as well. Here's the mass flow. And let's take a time plot at the inlet. The mass flow is quite constant at 200 kilos per second. Of course, we expect that when that was our steady state condition at the beginning, but it then varies somewhat according to what we take out at the downstream end. But we see the variations at the inlet end are very much smaller. It's relatively constant mass flow in at the inlet end, even though we know it varies between 400 and 200 kilograms per second at the outlet end. So we can see that if we go to the outlet end, there of course it was a boundary condition that it should vary between 200 and 400 kilograms per second. So in the middle of the pipe we will also have some variations, but they are smaller there. And the closer we get to the inlet, the smaller the mass flow variations will be. The last simulation experiment we will do is breakage near the platform where the pipeline comes from. Again, we go back to our original case here and we reset it. And now at this boundary we will start out as before. We go full speed, we have 114.9 megapascal at the inlet pressure. But suppose that after just 60 seconds our pipe explodes, or there's a big hole in it, so the pressure at the outlet suddenly becomes only 1 atmosphere, which is about 1 to the power of 5. Okay, and then when that happens, we would think that down in Belgium they will close down the pipeline there. So let's say they find out after a while, let's say after 500 seconds, for instance, they still take out as much as they can from the end there, but then they realize, hey, something has happened here. So during the last 3 minutes or so, let's say up until 700 seconds, they go down to 0. They no longer take out any gas at their end. We can change the settings slightly also. Instead of having 100 cells, when the pipe breaks, it becomes quite dramatic near the break. So in order to capture that better, we increase the number of cells to 400. That will make the simulation slower, but we can just skip the simulation time in the video. So there it starts with the steady state first, and now it goes into the transient simulation. That's a bit slower, so we will just stop the video recording for a short while there. We are now around 8 minutes into the simulation. So this of course went much slower than when we simulated with only 100 cells, and it's also slowed down by the fact that there's more things happening. And then the integrator detects that, and it takes smaller time steps in order to get the desired accuracy. So this was about 1,000 times faster than real time, not 200 times faster than when we simulated with 100 cells. Okay, here we go. Let's look at the pressure now. Obviously the pressure at the beginning is as before, but then a very short time later the pressure goes down to 1 bar only at the inlet, and it stays high in the rest of the pipeline for a while at least. But as time goes by, this has an effect everywhere. And here we see the pressure starts to come up at the outlet end, and that's because they have now closed the outlet end. So the gas close to the outlet is distributed more evenly there. But eventually the pressure will start to go down in the whole pipeline. So after 24 hours the pressure has come down quite a lot, but there's still some pressure left. What happens to the velocity? Well, we see that of course the velocity before we started was as before, but then after we have closed, the velocity jumps up to close to speed of sound near the outlet. We can see that better in the time plot perhaps. Interestingly, the velocity is relatively constant actually during this time, but the density changes. So if you look at the mass flow, which is really the relevant parameter, let's look at the mass flow in the time plot. So now we have the mass flow by the outlet, and it jumps down to, of course it's negative here because it's backflow, it flows out at the inlet. So we are up to something like 4,000 kilograms per second, but that's for quite a short while. And after a relatively an hour or so, we are down to 1,000 kilograms per second. But that's still a lot of gas. And this is very relevant when we do safety studies, because the heat generated in case of an accident, if we have an explosion, so that the pipeline breaks, the rupture will then lead to gas flowing back to the platform, and of course we will have a horrible fire there if this catches fire. And how many kilograms of gas we get in per second, the mass flow, is obviously relevant to how hot it will be there. And these numbers come out of the simulation as we see here. And even after 24 hours we have a considerable amount of gas flowing back. We are then down to something like 400 kilograms per second. So still a very significant amount of gas flowing back from this pipeline. Some conclusions then from the transient simulations. They clearly reveal more information than the steady state simulations. Steady state simulations are often the best way to start to find out some of the things we can expect from our long subsea gas pipeline, but anything that changes over time can't be revealed by steady state simulations. So we saw that long gas pipelines have a lot of storage capacity, which is a very good thing during normal operation. The consumer can take out much more mass flow during short periods, and such load variations will be smoothed out by the pipeline's storage capacity. And this is a transient phenomenon which we study carefully with simulations. So if we have an idea of how much we can expect the consumer to take out during the next week, or how it varies between day and night and so on, we can make very good predictions for whether we have the capacity or not, and what we need to do in order to ensure the capacity. We can do that by doing transient simulations. We also looked at what happens in case of pipe rupture. It's quite standard to do such simulations in order to look at the fire safety on oil rigs, for instance. We need to know how much heat we get in case of a pipe rupture and a fire. And in that case, the transient phenomena is very, very important, because just after the rupture we get a much higher flow. We saw that than anything that will normally exist in the pipeline. So in that case, the storage capacity is a bad thing in case of an accident, and we need to simulate that as accurately as we can in order to know the heat load in case of a fire. We hope you enjoyed the video. You can go to this internet site and get more information. You can also find a link there to the first SeaPipe video. You can also download free copies of the SeaPipe report, which was for the steady state simulations. And you can download 2 books describing the theory behind the simulations. Thank you for listening.